No, we're not getting that lucky. That's true. No, because I got that and the other class to come back to, and they're having a test Wednesday. So anyway. Okay, all right. So we've been talking about energy and work, and now we want to look at potential energy and how energy is conserved. So we've already talked about work. Doggone it. We've already talked about work. We know that work, if it's a constant force, it's the force times the distance cosine theta. If it's a varying force, we know that work is the integral of the force with the limits of x final and x initial. It's force dx, right? It's the integral of the force with respect to the change in position, okay, or position. And now we're going to look at work in the form of gravitational energy, okay? Now we've already actually discussed this and looked at this. Again, if we take the work equation and substitute mg and turn that into y, there you go. And we call it potential energy, gravitational potential energy, okay? All right. So the equation changes a little bit, but y'all, that really shouldn't stump us, because what is that right there? That is weight. So this should not, it really shouldn't be that difficult to grasp, because remember, y'all, weight is a force, okay? And so it shouldn't be, even though it looks different, and it does kind of look considerably different, I guess, because it's mg, but still we know that's weight. And of course the units are going to be the same, you know that. Remember we talked about this very beginning of this chapter, that the units are going to be the joule, just like it is for kinetic energy, just like it is for work. So, but now what we need to do is we need to look at the relationship between potential energy and work done by gravity. Now remember we talked about this the other day, that if we lift an object, if I take this stone and I lift it, I'm doing positive work. The work done by gravity is negative, right? Because I'm moving away from the center of the earth, I'm doing the work as I move the stone upward. So work done by me is positive, work done by gravity is negative, okay? Well, that work done by gravity is called potential energy, okay? And so notice they tell us here that the work done by gravity is actually less than zero. So as positive work's done, potential energy decreases. So as I'm doing positive work, potential energy, I start out with very high positive, low potential, but when I get to the very top and stop, then potential becomes what? Very high, doesn't it? And work or kinetic energy basically goes to what? Zero, okay? And so we need to understand this, and this is a little bit, I hate to say the word confusing, because I don't want to plant a seed in your head and think, oh, it's confusing. It's not. It's maybe a little ambiguous maybe. So when we look at the potential energy, when we compare potential energy to work, this is how we should write it. Let me just go back here. So we have the work done is equal to the negative change in potential energy. So if we're going to start comparing work to potential energy, and you say, how does it come to that? Well, when we look at the change in position, as you move from this point to this point, notice that your potential energy is decreasing, okay? So if you look at gravity, and I let the stone go, it has very high potential where it's way above the floor, but when it gets really close to the floor, the potential almost or practically goes towards zero, right at zero. When it hits the floor, it is at zero because it's on the surface, okay? And so that's what they mean by this. And we can write this equation this way too. Negative change in U. But now look at how they define the change in U. They define change in U, potential energy, as U1 or U initial minus U final, instead of final minus initial. That's how we get the negative change in potential energy. Does that make sense? And really, if you think about it, it has to be that way because of the demonstration I just did with you. Okay? Okay. So let's put this together now. Let's put kinetic energy and potential energy together. And we call it the conservation of mechanical energy. And typically we write it this way: E is equal to K plus U. Okay? And E is mechanical energy. Sometimes you'll see it written ME in physics books. ME, mechanical energy. Okay, it's the same thing. E, ME. Probably be a little bit better to use ME, because if you just say E, well, that's energy. Well, there's all kinds of energies. You've got internal energy. You've got the energy of friction. You've got kinetic energy. You've got potential energy. Let's see, what else we got? Let's see, I said internal, friction, electromagnetic, thank you, yes, electromagnetic energy. And you'll see this when we get into next semester, that this equation will get pretty long, where we'll throw all these in there. All right, okay. Now, I'm telling you, when you get into thermo, and most all of you will have to take thermo, it gets interesting, all right? It's amazing at how thermodynamics affects every aspect of our life, literally. Not just how we live, how we work, everything, how we play, everything. I mean, come on, y'all. Did you put a coat on this morning? Wear a long sleeve, wear a sweater? Yeah, why? Well, thermodynamically, it was pretty cool outside, wasn't it? Of course, that's a word we don't like to use. We should say lower kinetic energy or lower energy in the atmosphere, but we say cool, all right? Well, that affects us that way. It affects us everything. Everything mechanical is thermodynamically involved. Everything. It touches every aspect of our life, okay? Okay, so we write our conservation, and that's how I want you to write it. Notice this: only if gravitational force does work. It's not talking about other work. We'll get to other work in just a second, okay? So notice that and that's how you need to write it on your formula card, because when we look at other work, we're going to throw that into this equation. It doesn't really make it any harder. It's just another variable. That's all it is, okay? So look, if you take K final minus K initial is equal to U initial minus U final, you should get this equation right here, okay? You add U final to both sides, and you add K initial to both sides, and you get this conservation of energy equation. That is it. And now again, only when gravity, all right? This is an extremely useful equation. Remember I told you, as engineers, many times you're going to solve problems, if you can, from an energy standpoint or from a momentum standpoint. It's just a whole lot easier. Because why? Well, because look, we can determine weight, we can determine the velocity, initial and final velocities. It's more practical to do that. That's another reason momentum's useful, because of velocity. And then we can go on and find force if we need to find force, okay? All right, so it's very useful to do your problems from an energy standpoint, okay? When possible, and a lot of times it is. It's just more applicable. Just like when a state trooper examines a car accident, he's looking at energy. He's looking at how much energy. He's looking at the velocities and how much kinetic energy there was, okay? And then momentum comes in there too. Okay, we'll get to that later. So there's one equation. And again, here they're just showing you how, and we've already been over this and over this and over this and over this and over this. But now notice that the sum of these should equal 0, okay? The sum of these should equal 0, all right? In other words, the total kinetic should equal the total potential. And when you add them together, it should equal 0, okay? Because look, he's not going to gain energy from here to here. He's not going to gain or lose energy from here to here. How? How could he do that? Okay, yeah, I know air resistance, but it's not much, okay? Not this short distance. Now, yeah, falling from 10 miles up, oh, yeah, sure, there's going to be some energy lost there. And it's going to be lost to heat. That shuttle or that capsule is going to get really hot. Okay, and it helps to slow it down too. Of course, you don't want it to get too hot because it will melt. They've not made a metal yet that can withstand re-entry temperatures. That's why they have to re-enter at a certain angle. And they have to maneuver the craft usually and deploy parachutes. Okay. Columbia is a perfect example of that. Okay, all right. Okay, and again, here we see the example of the parachute when you have forces other than gravity doing work. So what were the forces here? Well, it's going to be air resistance, isn't it? So not only do we have kinetic, not only do we have gravity, but the force of gravity, weight, but we also have air resistance. So what does this do to our equation? All right, well, we know this equation already, that the work gravitational, notice again, work initial, gravitational initial minus gravitational final. Again, why? Because it has to be negative. It has to be negative. So, here again, they're just showing you that when it's just gravitational, okay, it should equal 0. Notice when you throw in, let's see, when you throw in, I think that's or air resistance, notice it equals H, okay? Now, so let's look at elastic potential energy, okay? So when we look at elastic potential energy, this could be a spring. What about rubber bands? Would this work for a rubber band? Would this equation work for a rubber band? No, it would not. And why? That's exactly right. It's called rheostasis. I actually have a lab. I never have done it yet. I've thought about incorporating it when we're doing energy, where you can actually calculate the rheostasis of a particular rubber band, by stretching it, measuring the change in displacement as it stretches and goes back to equilibrium. And you start with equilibrium and then stretch it out with a mass and let it come back. Well, it's not going to go back to the original position. And you could actually measure the rheostasis of any rubber band you want to measure, because it won't. That's why they eventually break. Well, you all know a rubber band's not going to last forever. That's why I'm not crazy about bungee jumping. That sucker's eventually going to break, y'all. I mean, come on. It's eventually going to break. So you better pray to God if you do that the people that are, selling you the ticket know what they're doing, and they're changing those straps out. They should know how many times you can do that and how much weight before it starts getting to the breaking point. But then you have to deal with, well, did the guy making the bungee cord do a good job making it? Maybe he had a bad weekend and he come in and made a Monday bungee cord or a Friday bungee cord because he was ready to go party or whatever. You've heard that old saying. Well, that's true, y'all. You don't want nothing made on a Monday or a Friday. And I hate to say that, but that's the truth in many cases. Okay. But yeah, so this would not work for a bungee cord. All right. I mean, this is only for springs. Okay. But notice, y'all, this looks very similar, doesn't it? Remember when we had that right there? Look, it's the same equation. And again, where did we get it? We get it from integrating. We get it from taking Hooke's law and integrating it. Remember that? When we integrated it right here, we wind up with that right there. Okay? All right? So we just integrate Hooke's law and we get that equation. Again, still joules, and they're talking about muscles and whatnot. Okay? Now, work done by spring. Again, now here they do it horizontally. We don't have to do it horizontally. Today you're going to do it vertically. It really doesn't change that much. The only thing is when you're doing it vertically is gravity. Okay? You've got gravity pulling on the mass, and it's going to be what causes the change in displacement. Okay? Whereas here, the change in displacement is totally done by the spring, or by you stretching it and then releasing it. Okay, today we're going to put masses on here, and it's going to oscillate. Okay? I mean, I think you know that. You know what's going to happen. All right? Just by me touching it, it's oscillating. Okay? So gravity and the springs doing most of the work here. Well, we apply a little bit of kinetic energy when we pull it down. There's actually 3. But it's not as much as the other 2. Quite as much anyway. All right? Okay. So notice the change of displacement. Let me ask you something here too. Where would velocity, all right, here it is at equilibrium position. All right, here it is stretched. Where would, and notice it says as the spring stretches, it does negative work on the block. Notice they said the spring. But if I'm stretching it, what am I doing? If I'm grabbing the block and pulling it, what am I doing? Positive work. So I'm doing positive, the spring's doing negative. Does that make, everybody, that makes sense, doesn't it? Because you know, if I let it go, what's it going to do? It's going to go back up. So the force of the spring has to be in the opposite direction, all right, restoring force. We already covered that. All right, but let me ask you something. What's going on right here as far as acceleration and velocity at this point? If I pull that block out and let it go, where it is positive, that's right. Where will velocity be maximum and acceleration be 0?
Right before you let it go, or the moment you let it go.
Okay. All right. Okay. Okay. Y'all are hitting in the right direction. So in other words, if I pull this block and let it go, is it going to stop when it hits the equilibrium position? No. It's going to compress a little bit, isn't it? But then it's going to stop momentarily, right? Okay.
That's one of the maximum velocity.
Right at the peak, isn't it? And what happens to acceleration? It starts reversing at that point. That's good. That's very good. Okay. So as I get here and let it go, and it goes beyond the equilibrium position to the negative position, once it gets compressed, right at that moment, acceleration becomes what? Negative. But it's positive here. Well, let me ask you something. Where would velocity be in actuality? In other words, then, when it stops, what is velocity? 0. All right, where's velocity maximum?
Or right before it starts compressing.
Which would be at what?
Equilibrium.
Very good. That's exactly right. So let's analyze this now. Let's think conceptually. We pull our spring down and we let it go. All right, now watch it. Pull it too far. All right. All right, let me just do that. All right. Okay, so maximum velocity has to be where? We pull it, we let it go, it comes back here, compresses. Maximum velocity has to be here. What is the acceleration there? 0. That's right. Okay? Does that make sense? So acceleration is going to max where? It's actually going to be going in the opposite direction here. And when it gets here and fully compresses, acceleration is going to be going in the opposite direction when it's fully compressed. So acceleration is greatest beyond... Actually, it's greatest right after I let it go, isn't it? It's really accelerating. And it hits 0, and then it starts doing what? Decelerating till we get to compression, and then it switches directions, and it goes back to maximum for a brief moment, doesn't it? Does that make sense? Okay? So you need to think about that. You know, if you're using springs, and you need to, you know where the equilibrium position of a spring is, but yet you need acceleration on that spring at certain time intervals and at certain locations. You need to think about conceptually where that's going to occur. It's not going to occur there's no acceleration when it reaches equilibrium. It's max velocity. Okay? And you say, well, why do you want acceleration? Well, come on, guys. Force times mass times acceleration is force. So you may need a certain force at a certain distance from equilibrium position on both sides of that spring, and so you have to think, oh yeah, acceleration is occurring here and here, and it's occurring here and here, but it's not occurring there. Okay? All right? It's changing direction at both far extents. Okay? So that's something you need to remember. You need to kind of keep in the back of your head when you get into engineering school, because that'll become very important. All right, so we look at graph of elastic potential energy for an ideal spring is very obvious when the spring is compressed, when it is stretched. Notice where it's 0. Okay? Right in the middle. And notice too, it's never negative. It's never negative. Okay? All right, remember now. Yeah, work is, yes. Work can be negative. Kinetic energy can't. But work can be negative. And remember, that's the net work. Or, well, we can even look at total work. Total work can be negative. I mean, if you're giving off energy, let's say something's cooling. Well, what's the work going to be there? If something's cooling, but again, we got to keep, well, now what system are we talking about? If we're talking about the object, the work for the object would be negative. But if we're talking about the air around it, the work for the air would be what? Positive, like a hot piece of metal. Okay? Does that make sense? And there again, in thermo, that's where it gets confusing if you're not careful is, okay, which is the system and which is the environment. You can make whichever one you want the system and whichever you want. For example, we got a heat and air unit. I can make that the system. And the air, the environment, which is normal. But I can turn it around. I could say, okay, let's make the air the system and let's see what kind of effect all of these bodies in here with temperature, giving off, heat, thermal energy, how would it affect our system? And y'all, you know good and stinky well it does. Have you ever been in an auditorium when it's cram-packed in the summer? If the maintenance dude didn't turn the air down, what's it going to do? It's going to get what? It's going to get really hot, isn't it? Okay? You ever been in our wedding, when we got married, we had like, Lord of mercy, it's like a 250-seat church, and we had probably 350 people in there and had candles everywhere. And it was July the 2nd. And I was soaked time of our wedding ceremony. I mean, soaked. It was running down the side of my face, running down. I was a river running down my spine on my back. I mean, it was hot. Okay, I mean, really. So that in that case, the environment became the system because it affected the heat and air unit. Okay, so that's interesting when you look at that. All right, let's move on. All right, so conservative forces and non-conservative. Conservative forces do what? You do need to know this. Allows conversion between kinetic and potential. Gravity and spring force are always conservative. Okay. However, when you look at work done between 2 points by conservative force, notice this. It can be expressed in terms of potential energy. It is reversible. Okay. Is independent of the path between the 2 points. Notice that. That's really important. And then if 0 is the starting and ending points, they're the same. Okay. All right. And notice here they talk about how do we define a non-conservative force? Friction is probably the number one non-conservative force. That's the one we typically think about the most.
Any energy going into that force doesn't come back.
That's right. That's right. Typically it'll be lost as heat, won't it? Yeah. Yeah, friction, I mean, come on, you put your hands together and you do that right there. Your hands are putting more energy, the muscles in your arms are putting more energy into your hands than what you're getting out because you feel your hands begin to heat up. Well, you're losing some of that to friction. It's lost as heat. Okay, that's typically how we say it. Now, we've always been told that energy is always conserved. Well, it is, but sometimes in the transformation of it, we can't get it back. Just like your engine on your car. If you could make a 100% efficient engine, wouldn't that be great? Well, then you got to do away with friction. Okay? And that's why, cars, even though you can make a car with high gas mileage, you're still going to lose some energy to heat because of friction in the engine and because of the combustion process. It's just, you just can't get away from it. Okay? Now, electrical transmission, that's another thing, electrical energy. They do have now the superconductive electrical transmission where you don't lose any. You can transmit electrical energy at 100%. Now, it has to be done at low temperatures. That's the only kickback. If they could ever get it to where it's way above 0, we'd probably do away with all electrical grids, all electrical transmission lines, as we know it now, which would be great because how much energy that the plant produces do we actually get? We don't get it all. even in the as they pass it through transformer or substations, you still have some loss. Okay, so it's not perfect. Okay, it's not perfect. All right, let's move on. Okay, all right. So what about this is our law. Now notice this here is the law of conservation of energy. The law of conservation of energy. Notice that if you take kinetic energy and the change of potential and the change of potential internal energy, they should all equal 0. If I solve it this way, if I solve it for delta K, then it's going to be equal to what? Negative change in potential, gravitational potential, and negative change in internal potential energy. Like chemical. Chemical would be considered to be an internal potential energy. Okay? There's CPE and GPE, gravitational potential and chemical potential. Okay? Okay? And spring is also internal. Okay? All right. So there's your law of conservation of energy equation. And like I said, well, you know this. You should know this from high school. We don't create or destroy, but it is conserved. But sometimes in the transformation process, it can be lost as heat. Okay, we'll get to that when we get next semester. Okay. All right. Okay. And that's where we want to end today. Okay. All right. Okay, go ahead and, whoops, sorry.